one is basic, and really it's if you ever threw a tennis ball against the wall, you'd see the same exact thing, where anytime you hit something or bounce something, it will always have to bounce off the same angle it went in at. And so it's still with waves, you know, anytime you've used a mirror, you notice that. It has to come in and out at the same angle. Now you could also use this idea with pool, right? If you're going to hit a bank shot or anything, what you do is you kind of line up and look at the perpendicular line to the wall, okay? And then split up the angles to figure out what angle it needs to bounce off at when you hit it in at an angle. So it's still the same thing. But obviously with light, this works the same way, where you have to look at the normal, okay? And you need to train yourself to always find the surface and find what's perpendicular to it, okay? And then with respect to the normal always is when we talk about equal angles. But this is also for sound, okay? So I actually have an example of it. It was a beautiful sunny day on the college of Ithaca, or on the campus of Ithaca College, and
what college is that?
Ithaca College. So
What? American?
Ithaca College. Ithaca
In New York?
College.
What is
Yes,
place?
upstate New York. Same town as Cornell. Cornell is in Ithaca, New York. Okay. Now, here's an aerial view of Ithaca College. Now, there was a certain student that had to go to his 3 o'clock class. It's about 2:30 or so, maybe 2:45. But it's a beautiful sunny day, which doesn't happen often in upstate New York. So, his friends are playing outside, including his roommate. And so he decides to play music and, you know, have his speakers pointing out the window, crank up the music, let his friends enjoy, and then he realizes he has to go to class. So he starts heading out, and his friend, you know, his roommate's already outside, so he figures he can go inside and you know, he'll keep the music going. And as he starts walking out of the dorm room, or out of his dorm, he hears the song change to a really inappropriate rap song, okay? And he keeps kind of walking and trying to think what he's gonna do, and he's like, you know, should I go back and change it? But his roommate was outside anyways, and as he walks a little bit closer to the parking lot, the sound gets a lot quieter. So he says, all right, well, you know, it'll be okay. He sees all these people over here because it's a nice sunny day, and this is where he needs to go, okay? And so there's all these students hanging out, but he can barely hear it once he's in the parking lot. So he walks a little bit closer and across the parking lot, and then when he gets closer to the building, he starts to hear the sound again. And it gets louder and louder and louder. And right when he's in front of the building, where everyone else is hanging out, he can hear that very inappropriate rap song clear as day and just as loud as when he was outside his dorm. Alright? So, the problem was this. When the sound, there's a nice big long communications building right here where many TV producer and directors have come from. Alright? And when he was over here, there was no place for the sound to reflect to bounce down. However, over here, if you follow back and think about equal angles, turned out it was using that building perfectly to bounce off and go exactly where he is. And so he looks around, everyone's kind of wondering who's the idiot playing that song, and he just says, man, that's terrible, and runs into the building as soon as possible. Alright? So anyways, the next time you want to play very inappropriate rap songs, think about the law of reflection. Okay? Okay. Alright. Now, one other thing for reflection. Thank you, sir. With reflection, realize that there's 2 types of reflection. Okay? A regular image or just diffuse. Meaning, if I look in a mirror, yeah, that's reflection, obviously. Okay, but then I'm seeing a regular image. Especially I have a smooth surface. I can see a copy of another image on that. But me looking at you right now is reflection also, right? Because it's not that you emanate light. Okay? Right now I see you because light is bouncing from the lights here, it's bouncing off of you and going to my eyes, and that's the way I see you also. So both are reflection, okay? If we're talking about a mirror, that's a regular image. If we're talking about anything else, that's a diffuse image, okay? And it's still reflection, okay? And it really has to do with the normals. If you have a flat surface, okay, the normal at every point, if you have 3 rays of light here, okay, every ray is going to hit and bounce back off at the same angle because you have a flat surface. But if your surface is different, and there's all different normals all over the place, right? Here's a normal here, here's a normal there, there's a normal there, then you're going to get a different image. Okay, the light's just going to bounce everywhere, and that's how I see your image.
Is that why, like, you know those mirrors when you go to like a fun house and they're like curved?
Yes. They have different normals. Because it's curved, you're going to have different normals, and the rays are going to converge in different spots. Yeah. Cool. Okay, I'll pause there and let you come. If reflection was the bouncing of waves, refraction is the bending of waves. Again, don't copy this picture. We're going to do 3 pictures in a row next slide, or sooner or later. So if reflection is bouncing, refraction is just bending. Anytime a wave travels between 2 different media, okay? Specific, most of the time with light, but anytime a wave travels between 2 different media that one is thicker than the other, there will be bending. Alright, I want you to think about a car that's going to go off-roading. You ready? And if you look in the parking lot, I think a lot of people think about a car going off-roading. So, we have, here's a car. Let's say this is asphalt, and this is going to be grass. What's faster, the asphalt or the grass?
Asphalt.
Asphalt, right? So, we drive up from the asphalt to the grass, from a thinner to a thicker, or from a faster to a slower medium. And as soon as we hit, what tire is going to hit first? Passenger or driver's side?
Driver.
Passenger side, right? I pull up and the passenger side tire is going to hit the grass. Alright? As soon as that tire hits, you have one tire that's slower than the other. Does that make sense? I have my passenger side tire is going to be going in the slower medium. My driver's side is going to be in the faster medium. So what would happen to that car? Or truck? It's going to turn, right? Because you have this faster one, it's going to turn. Now once that second wheel hits the grass, now they're both going slower. Okay? Then it'll go in a straight line again. So only at that surface, only at that line between the 2 points will you see the turn. Once both tires are in, it goes in a straight line again. Alright? This is exactly how light works. Okay? When you see an image of something, you have rays coming down. Well, one ray will hit the slower surface, hit the slower material first. And that is how an image gets bent. Alright? So examples. Ever notice, like, if you were rowing, you'd notice an oar is bent in the water. You know what I'm talking about?
Field trip.
Field trip, yes. Let's go canoeing. Alright. So here's the idea of refraction. And we've seen this before. Now, I have an experiment. Pause for me for a second. Is the beaker going to get bigger, smaller, or I don't know, disappear into thin oil?
It's gonna get bigger.
I say it's gonna disappear.
Okay, let's find out.
I'll be the
You
rebel.
ready?
Yeah.
Are you recording? Okay, here we go.
I'll be the rebel.
Where'd it go? It's bigger.
Did you seriously say where'd it go? Oh, I was right. What?
It disappeared, I told you.
I could still see it.
No, everybody thought it was, no, it disappeared. You can't even freaking see it. Everybody thought it was.
There we go. So it disappeared.
I thought it was gonna disappear,
Do it
but
again.
it's not going anywhere.
Want me to do it again? All right. We'll do it again, but we don't need to record. Asking in different ways about these 3 scenarios. Okay, especially these last 2. And the idea is that I want you to understand as many ways as we can say it. So I might say something like, when you go from a thinner medium to a thicker medium. I could say from a faster medium to a slower medium. I could say from a lower index of refraction to a higher, or all vice versa. Okay? Thicker to thinner, thinner to thicker, whatever it's going to be. I will test you on that. Okay? So, however you want to think of it, I honestly think, again, think about, and obviously you can have this on your yellow sheet anyways, but think about the car. Think about wheels, 2 wheels hitting the grass. Okay? Or going from grass to asphalt. But make sure you understand, you know, and you can picture. It might be easier to do. Okay? Thinner to thicker. We just talked about it. It's going to hit, passenger side wheel hits first, and it's going to turn inward. Okay? Thicker to thinner. The outside, that driver's side wheels now, is going to hit the faster first. It's going to turn outward. Okay? If you have 0 degrees, an incident angle, we'd say, of 0 degrees, then you'd have 0 degrees of refraction. Okay? If both wheels hit the same time, they would both slow down at the same time. You wouldn't have any turning. Okay? But these are the 3 scenarios you need to know, and I'm going to definitely test you on it. Maybe even on the final exam. Alright. Moving on. With refraction. This is the actual equation you want to know. Actually, these are 2 equations. Okay? This is more just talking about how light travels through each substance. Here's the equation we call Snell's Law. Alright? And I actually even give you different indices of refraction. So the idea with that corn oil is that the corn oil basically had the same index of refraction as the glass. Okay? I googled it. Like, this is just one index of refraction of one type of glass. There's a million different types of glass indices of refraction because of the way they make the glass. So I'm not sure if the corn oil had an index of refraction of 1.61 or if it was a different type of glass. But you want to copy all this down, especially the indices of refraction. Yes, you'll need to know that. We're going to practice this equation a little bit, how to solve for the angles, okay, in case we forgot how to solve for angles. And you need to know that equation. I'm going to give you a worksheet on it today. All right, we'll pause there. We have one as the incident angle, meaning what is moving, it's leaving, okay? The refracted angle and the number 2 will always be what it's going into. So, if we have light that's traveling from air to water, index of refraction, N1 would be air, okay? Whatever the angle is, we plug in there, all right? N2 would be water, so we'd have 1.33, all right? And then some angle would be going there. We just would be solving for one of the 4 things here. Alright, and most likely it's going to be you're solving for one of these angles. We will do it in a little bit, but remember, the idea is that you have to inverse sine, right? To cancel out so you can get an angle by itself, you're going to have to do inverse sine to both sides. This is saying that if you had an unknown substance and you didn't know the index of refraction, you could do the speed of light, which is c, right? We talked about that. What is the speed of light equal to? What's the number? 3.0 times 10 to the 8. Yep. Divided by the velocity that that light traveled through a substance. Now, quite honestly, it's probably going to be more the other way. And on the worksheet I give you today, it'll be the case where you're going to solve for v. You're going to solve for the velocity that the light travels through a substance. Okay? So the idea is that when light travels through air, air is basically the same thing as space. Okay, really the index of refraction of air is like 1.003, but that's close enough. We don't really care that much about it. Where water, meaning it's going to be, if you did the speed of light divided by 1.33, you figure out how much slower light travels through water. If you think about that, then a diamond will be 2.5 times slower. When light travels through that diamond, it's going to be 2.5 times slower than light traveling through air and through space. Okay, so light can travel slower in different substances. That's why we have things refracting. Alright, so that's pretty important. Alright, so you need to know these equations. Yes, you'll need to know how to do this, and you will need, a lot of times you'll be solving for V here. Okay. Alright, now, here's a pretty cool thing about refraction. Remember that when you go from thicker to thinner, thinking about that truck going from grass to the asphalt, all right, you're going to have, it's always going to bend further away, right? So if I have a ray of light that's coming from water to air, that ray of light is going to bend outward, okay? If I go a little bit further out, it's going to bend even more. A little bit further out than that, it's going to bend even more. Well, sooner or later, because this angle is always going to be bigger than that angle, what you're going to notice is there's going to be one angle here that causes that to be 90 degrees. Okay, which means basically the light is going to get trapped within the surface. Alright, has anyone gone diving? Alright, have you ever been, or even if you just dove underwater and looked up, if you look from underwater, if you look up, you're going to see just above you, you'll see it above the surface. Okay, you'll be able to see, you know, if you were out near a boat, you'll be able to see the boat if it was right near or whatever. But you're going to see just a circle of it. And past that circle, okay, if you look further out along the surface, you'll see light actually bouncing back in. Okay, whatever you're going to see further out is going to be a reflection of the bottom of the pool or the ocean or whatever it is. You could do the same thing if you were at an aquarium. All right, if you look to the side of, you know, the fish tank and you look up, what you will see is some angles where you're going to see a reflection from the surface of the water back down into the aquarium. So it'll be literally like a mirror, okay? And we call this total internal reflection because anytime you look past the critical angle, okay, anytime you're having a ray of light that's going from a thicker to a thinner, and you look past the critical angle, that surface will now act just like a mirror. The light will get trapped in the surface. Okay? So as with water, with any surface, when you go from thicker to thinner, you'll actually see light getting trapped in. Okay? And the reason I say theta i's and theta r's is because then it's just like a mirror. Law of reflection says it's going to be equal angles. Alright, so you don't have to copy that down again. Alright? But again, I will test you on reflection and refraction and critical angle. Just remember that if I say, what's the critical angle of water to air, I'm not asking for 90 degrees. Although I'm sure I'll give you that option in multiple choice. Okay? But the critical angle wouldn't be 90 degrees. The critical angle would be the angle here that causes that to be 90 degrees. Does that make sense? And I know people will make that mistake and put 90 degrees as their answer. But don't. Alright, the critical angle is the angle here that causes this ray of light to turn 90 degrees. Okay? Do I need to pause or are we good to go? Pause? I'll pause. Pause. An example of this refraction. Can we see that? Can we see this? So we have glass here. And then it's going to go from glass to air. Because this is the circle here, there won't be any refraction at that point. It's going to go head on. But now when it goes from the glass to the air, it's going to bend. Want me to turn the lights off so you can see it better? Okay. So here's a ray of light. And the incident angle is about 25 degrees. The refracted angle is about 35 degrees. Alright? They change it. Now here's close to 40. And what you're actually seeing is that there's going to be some imperfections. You see a little bit bouncing back down already. Okay? But you're actually getting pretty close to that critical angle where I think this might be actually just some imperfection, but it's going to get trapped along the surface right there. Okay? So here's at 40 degrees. So if this is a critical angle and there's just somehow an imperfection allowing a little bit of light out there, what's going to happen when we get to 50?
It's going to be on the line. 90 degrees.
Well, we're saying this is a critical angle. That would be this. So we're saying this is about 90 degrees, or it's just about to be 90 degrees. Either this is an imperfection, and it's really most of it's trapped. But what about when we get past that critical angle?
It'll go back on there.
It'll go below 90.
Right. It'll be a reflection, just like a mirror. See that? And so now you got 50 degrees, 50 degrees, essentially it's going to be the same thing. So now it's become a mirror. And that's exactly like water, okay? any other type of surface, any other type of material, you get a critical angle. Where light, and we call again, total internal reflection. Past critical angle, the light is totally internally reflected back in. Okay? Alright, now, have you ever gone swimming at night in a pool that's lit up? Notice how the light kind of seems to be trapped in the water, it kind of glows? Yes, no?
Yes.
Okay? The reason it looks like the water is trapped, or the light is trapped inside the water, is because the light is trapped inside the water. Okay? So what we have is, think of, most of the time the lights are going to be on the side, and that's going to be, for one, for safety. But you have the lights on the side because as the light bounces up, okay, if it's within the critical angle, okay, and water is about 48 degrees. So if the ray of light is hitting the surface of the water less than 48 degrees, then the light's going to escape. Okay? However, if it goes past 48 degrees, it's going to bounce back in just like it's a mirror. So that's why you'll see those pools seem to glow. Okay, these are my various summer homes that I own. Okay? Now, I think this one is my home in California, and this is, I forget, one of my
That one
homes.
kind of looks ghetto.
Now,
That green water's nasty.
well, the green water, I want to point something out though. So what they have a bunch of streams going in, right? And they have lights, but notice what's happening. The light is staying inside that stream of water the entire time.
Yeah.
So the fact that you have a small enough, for one, you want to have a thin stream of water, okay, or something needs to be thin enough. But the idea is that this keeps bouncing, okay? So as that ray of light stays in that stream, it keeps bouncing and being internally reflected within the water until it goes back into the pool, okay? This is like a fiber optic, okay? You know what fiber optics are? Like, have you ever noticed, they sell them at Spencer's, like the plastic hair you can shine a light out? You know what I'm talking about? They're in Christmas trees. Some Christmas trees are fiber optics, so you don't have bulbs on the tree. You just have a light at the base, all right? This is what fiber optics are. Does anyone have Fios? Does anyone have Fios?
I do.
Okay, Fios is fiber optic signal coming from Verizon to your house. Alright, and this is the way Fios works. You get this extremely thin piece of glass. And because you have a thicker medium, alright, glass is going to be thicker medium, and you get something that's really thin, when the light is shined, it keeps bouncing inside of the medium because it's always past the critical angle. Okay, so compared to cable, where, copper cable, you have electricity being turned on and off, on and off, on and off. You can lose some energy with really high frequency stuff with the copper cable. With fiber optics, you lose less energy. Okay, the light can travel a lot better through the glass than electricity running through a copper wire. So that's how Fios works. Okay, you have a piece of glass that's connected to your house, and basically there's Verizon's on this side flashing lights on and off, and it isn't until you get that 90-degree angle over here that the light can escape. Okay, if you notice here, look at the side of these fiber optic cables. Notice how the light's not escaping? It's only on the top part of it. Because it's trapped. It's totally internally trapped. You don't want, on fiber optics, you don't want light getting off out the side. That means you're losing the signal. This was my job before I was a teacher, where I worked at a big server farm where you had to run fiber optic cable to another machine, to all the computers. And you had to be careful because, for one, with a fiber optic cable, if you put your finger up, so we'd have a piece of this fiber optic cable and we had to put a plug on it, plug it in the computer. And when you strip all the insulation around it, you had this little piece of glass, and if you put your finger up to that glass, you wouldn't feel it pierce your skin. You wouldn't feel it until it hit a nerve, and then you'd realize you had glass in your finger, and you'd pull it away, and then you'd have broken glass in your finger that wouldn't go anywhere. Okay? So you had to be really, really careful with fiber optics because it's just this tiny, tiny piece of glass. And with it, when it's thin, it makes sure it can trap that light in. Alright, but you had to be careful also with fiber optics because For one, if you bend a cable too much, any kind of cable, if you bend it too much, you can lose a signal. Now, obviously with glass, if you bend it too much, you could break the glass. But even if you didn't break that glass, and it was a mixture of glass and plastic. But if you bent this glass a little too much, the signal could then be could be less than the critical angle, and you could lose that light. The light could escape. Okay, so you had special turning radii you were given. With that cable, you could only bend it that much. If you bent it any more, you'd lose a signal or break the glass. All right, now, what are the 4 C's of diamonds, ladies or men? Cut, carat, color, and clarity. Right? All right. Cut is important because we said a diamond has a very high index of refraction. So if you've ever put a glass gem next to a diamond and they're cut the same way, the glass is going to, the light's going to travel through it pretty easily. That diamond is going to seem like it glows. It seems like it has its own light. Again, just like the pool, it's trapping light. Okay, because it's such a high index of refraction, the idea is that when a diamond goes in, especially through the top, it'll hit a point that'll be past a critical angle, so it has to bounce back. Down here, okay, again, it hits past the critical angle. So the idea is that with a diamond, the way you cut it, and also because you have a high index of refraction, 2.42, it will really trap that light, and you'll notice that diamond really seems to glow. All right? Where if you had quartz, because it's a lower index of refraction, light will escape it much easier because it would stay within the critical angle. It would be less than the critical angle and light would be able to escape much easier through all points. Okay? So that's how a diamond works. Now, also, I'm going to move on already. This is how a mirage works. I want you to think about the example of a mirage, and I'm going to turn the lights on here. Alright, with a mirage, think of the example. You're at the 4th of July parade. You look far off to see the marching band coming down. Alright? So you look far off in the distance, and you see that hot road, and it seems like there's water on it, right? Or you're out in the desert, you walk along, you see that beautiful blue water far off in the distance. You run up to it, and as you run up to it, the water disappears. Okay, that's a mirage, right? Okay. What you have with that is, on a really, really hot day, you're going to have really hot air right off the surface of the sand or the road or whatever it is. So right off the surface here, you're going to have much hotter air, so it's going to be much thinner and a lower index of refraction of the cooler air. So what you have, just like going from water to air, instead you have cooler air and hotter air. You have 2 different media. Now it's a subtle difference, so you really have to look far off in the distance. It's not going to be like a diamond where it's 24 degrees. But it's the same idea. So light can be internally trapped between 2 different types of air. Okay, cooler air and hotter air. So you look far off into the distance, right? And you see that beautiful blue water. What are you really seeing? What's blue and isn't water?
The cool air.
Nope.
Sky.
The sky. So what you're looking at when you see that beautiful blue water is actually a reflection of the blue sky up above. Okay, and again, you run up to it, you start going towards it, and as soon as you get closer to that image, you're going to be past the critical angle or within the critical angle. It'll be less than that critical angle, and now you can see the sand. Okay, that image is no longer going to be a reflection. So that's how mirages work. It's just light trying to be able to pass between 2 media. Okay, but in this case it's cooler air, which will be thicker than the hot air, which will be thinner. Okay? I will expect you to know how a mirage works. Okay? Alright. Now, also with a prism, same idea. The reason that you can get different colors is because the different colors actually refract at different amounts. Okay? Red light bends less than orange, which bends less than yellow, which bends less than green, and so on and so forth. So the reason that you get white, and obviously we all know white light is really all the colors of the rainbow. But the way we can split them up is because they bend at different amounts. When they travel through this glass, they're getting refracted twice because there's two surfaces. They're going to get spread out because the red can't bend as much as the violet can. All right, and that's how that rainbow, and that's how that spectrum is able to be seen. Okay, so it's just refraction and knowing that the colors bend at different amounts. All right, I'll pause there. Okay, we talked about waves already, right? Here's my wave. And light, actually, this is just one plane, right? This wave is only in one plane right now. Light comes off in all the planes. Okay, so you have this one, you have that one, you know, wherever. Every single plane, light will be traveling. So, when light waves, when you see glare, you know, if you were looking at the water and you see that glare, a reflection of the sun, you're seeing all the different waves and all the, all the different planes of that light wave, okay? And what you're doing is, so you have all these different planes coming off, and you get that glare, and it's tough to see. What polarization does is it allows only one plane to travel through. So a polarizing lens is only going to allow one of those planes through, okay? Just that one, say. Maybe that one. No, I gotta do it. There we go. All right, so a polarizing lens only allows, you can like it, only allows one plane through. Now, photographers will put a polarizing lens on when they're outside so they can get rid of any glare, right? Your sunglasses, your Oakleys are gonna have polarizing lenses to them. And actually, I think it was first I noticed with fishermen. With fishermen, if you want to get good glasses, if you're going fishing and you don't want to see the glare, you want to look into the water, you buy the polarizing lenses. Now, one polarizing lens alone is tough to tell if it's a polarizing lens or just a crappy pair of sunglasses you bought at 7-Eleven. But there's a way to tell. So this is a polarizing lens right here. Alright? And it might seem like it's just darkening, but it's not. It's just allowing one plane through. So right now, the light's coming through, and it's coming through one plane. I'm only allowing one plane of that light through. Alright? And the way you can figure it out is this. If I put a second plane on top, or a second polarizing lens on top of the other one, and they're both in parallel, they're only going to be a little bit darker. However, if I rotate and go to 90 degrees, they're going to block. So I have this at first. When I rotate to that, they're going to be blocked out. Okay? So I keep rotating around, and it keeps going back and forth. Okay? Perpendicular, parallel, and so on and so forth.
That's kind of cool.
It is kind of cool, isn't it? So, you know, if you wanted to tell if you bought a pair of Oakleys or a pair of Fakeleys, alright, you could have two together, have some polarizing lenses, and just turn them. And when they get perpendicular, if you can't see through them, you know they're not polarizing lenses. Or no, if you can't see through them, they are polarizing. Now, have you ever been driving and noticed, you know, looking at your car stereo, you can't really see it? You kind of have to tilt your head to see the stereo when you're wearing sunglasses? That's because the light is being given off as a polarizing, or it polarized in one direction. So you have to tilt your head until you can see the picture. My mother-in-law, okay, she's come to me a bunch of times where she's been taking pictures of the kids, and then she goes, my camera's broken. Because every time she tilted it, she couldn't see. Well, the reason was the display, okay, that LCD display is only being given off in one plane. So when she kept tilting the camera this way, it was now perpendicular with her sunglasses and she couldn't see the display. So I told her to take her sunglasses off and it would work. Alright? Cheaper, you know, some cell phones too, if you're looking at your cell phone and you turn it, you all of a sudden can't see the display. That's because you have the display coming off on one plane and it's now perpendicular with your sunglasses. Alright? Do you know what I'm talking about?
Nope.
No? Never?
Nope. I don't
Really?
wear
You must wear cheap sunglasses.
I don't wear glasses when I take pictures.
There you go. Okay. if you also maybe noticed, like with some cars, you're driving along, you're wearing sunglasses, you'll see like these checkered marks on your glass. Okay, and you'll see a kind of a checkered marks. Those are polarizing. The glass is polarized, and if they're only polarized in one direction, that would be really bad, because then if you turned your head the wrong way, you wouldn't be able to see out the window. Okay, but you'll notice that some windows will be polarized, and you'll see those checkered marks when you're wearing your sunglasses. Okay, so that's what polarization is. All right, now one more thing just for fun. All right, we get these perpendicular. All right, and now I take a third one and I stick it in between the two, and notice, can you see that when you rotate it? You can actually let light back through. Cool, huh? See? Okay, all right, that's it.